Proton-proton chain reaction is when the temperatures are high enough and the energy, speed is high, they collide. Two fast-moving protons overcome electrostatic repulsion and fuse together. The deuterium created in step 1 collides with another proton forming helium-3. This is a light isotope of helium. This step occurs faster. Helium-4 is an end product of proton-proton chain reaction. This process will occur in the core of a star. Outward forces are from the fusion, while inward forces are from gravity. When fuel runs out, the core cools, causing the end-out hydrostatic equilibrium. The inward collapse causes the core of that star to rise to 108 Kelvin, 6 times hotter than the core now. Heat builds up in the core to ignite helium fusion in a process known as triple alpha process. This process occurs in a star when it reaches the red giant phase, or when temperatures are about 100 million Kelvin. This process fuses helium nuclide together to form carbon to helium. For nuclei collide to produce beryllium-8. The beryllium-8 collides with another helium for nucleus to create carbon-12, releasing 7.275 MeV of energy. CNOAK. The carbon-oxygen cycle happens in O, B, and A-type stars. It starts with the collison of hydrogen with a carbon-12 atom to make nitrogen-13. Nitrogen-13 decays to carbon-13. This collides with more hydrogen, producing nitrogen-14. Nitrogen collides with another hydrogen, making oxygen-15. Oxygen-15 decays to become nitrogen-15. When this is struck by a hydrogen atom, it releases a helium for nucleus. The cycle then repeats. A star is formed by a nebula. Nebula then contracts and makes bigger clumps of dust. The clumps of dust is made by electromagnetism forces. Protostars are made in litters like kittens. This is how the stars are made. There's a few different types of stars. Brown dwarf stars are low in mass, less than 0.08 solar masses. Stars like our Sun have a mass around 0.08 solar masses. Bigger stars, like Betelgeuse or Alpha Centauri, they have a mass above 0.08 solar masses. Brown dwarf stars will stay the same size throughout their lifetime. Our Sun will last a pretty long time, around 10 billion years. When a star is dying, the star will go through a helium flash. First, the Sun will run out of hydrogen. The hydrostatic equilibrium will be lost. Right now, the Sun is off of the main sequence and the Sun will squish out. Then the star starts the helium flash. The Sun uses its helium fuel to keep in equilibrium. It doesn't last a long time. The red giants become unstable as energy rushes out. Each pulse throws material into space. White dwarfs are the core of the stars, or they can detonate as a Type 1 supernova. Type 1a supernovas occur when a white dwarf is in a binary system with a heavier star. It needs to be close enough to the star to reach the Chandrasekhar limit to be launched from the system. The lifespan of large stars is estimated to be about 10 to 20 million years. The temperature is 10,000 to 20,000 Kelvin. The color of the stars can be a white color or a blue color. D-type stars die faster than G-type stars. It has 8 solar masses and uses fuel fast. Near the end of its life it dies with a supernova. After a Type 2 supernova, a medium-sized star turns into a neutron star. But a high-mass star would turn into a black hole. When we need to find a new star to live on, we must look for an F or G-type star. These two types of stars are the most suitable for life to develop. Bigger stars will die too quickly, but smaller stars have a lot of potential radiation. Smaller stars also have bigger solar flares, which makes them really dangerous. The temperature on F and G-type stars are also not too hot. These stars has a habitable zone closer to the planet.